Call a three-term, strictly increasing arithmetic sequence of integers special if the sum of the squares of the three terms equals the product of the middle term and the square of the common difference. Find the sum of the third terms of all special sequences. Okay, so this seems like a pretty, very complicated looking definition of what's going on here, and then the task that we're actually assigned here seems to be, I guess just complicated. But I'm just going to take all the information that's given to us, translate it into mathematical statements, and then maybe make a little bit more sense of exactly what it is we're being asked to do. And maybe the set of equations that I have or set of relations that I write down, hopefully when I write them down, a new idea will come to my mind on how I'm actually going to solve this. Okay, so a three-term strictly increasing arithmetic sequence. So these will look like the following: a plus d, and a plus 2d, where d is strictly positive. And they're integers, so a and d are also integers. And it's special if the sum of the squares of the three terms equals the product of the middle term and the square of the common difference. Okay, so the sum of the squares of the three terms is that, and this has to be equal to the product of the middle term and the square of the common difference. So if this is satisfied, then we call the sequence special, and we want to find the sum of the third terms of all special sequences. So essentially, when I look at this, I'm thinking we probably just need to solve for all possible values of a and d. That'll give us all the possible special sequences, and then look at all the third terms. This is the approach I'm going to take. I'm assuming at this point that we will be able to solve for all possible values of a and d in this relation, but maybe there's something special is going on. Maybe something happens here where we aren't actually able to solve for a and d in each case, but we can solve for these third terms. I doubt that's going to be the case. So in order to solve for a and d here, should I just expand both sides of this and see if we get a lot of cancellations? I'm not totally sure that's the best approach. The square of the three terms, the sum of the squares of the three terms equals the product of the middle term and the square of the common difference. So the thing that's a little bit strange here is that this is a cubic term of order 3, and everything over here is quadratic, so I don't see that there's going to be any nice cancellation. I really don't see there being nice cancellation. Although in some sense it does put restrictions on how big a and d can be, right? Given that this is quadratic and this is cubic, this puts like a limit on how large these things can be before one of them outpaces the other. Huh. Maybe there's something to be said about factors of one side versus the other. I mean, I'm going to expand everything, but I don't think it's going to lead to anything useful. Well, maybe it will. I mean, I know there's not going to be cancellation, but there are going to be groupings of things over here on the right, on the left-hand side. You know, we could just start trying to guess some values here. I suppose for any fixed value of d, this is simply a quadratic expression for a. Maybe this is how we go about it. Fix d, which is an integer, and we also need a to be an integer. Okay, so this says that a is equal to so I need the thing under here to be a perfect square. And I also need that sum and or difference to be divisible by 6 and positive. Wait, I don't need it to be positive, no. The number a doesn't need to be positive, but the number d needs to be positive. Okay, let's look at this discriminant. Let me make sure I did the algebra, the simple algebra correctly here. I don't want to go on and carry a mistake through. Okay. So this is d squared times d squared minus 24. And I'm concerned with the square root of this thing. So I need d squared minus 24 must be perfect square. Okay. That will put bounds on, that'll give us essentially all the possible values of d. Because, you know, this is of course a perfect square for any value of d. D squared is a perfect square. For sufficiently large values of d, d squared minus 24, you know, if the distance between squares is greater than 24, then this can't be a perfect square. So that'll put a maximum value on d. So d can be equal to 5. I mean, we still have to check that the rest of this gives us an integer, but certainly we need the thing under the square root to be a perfect square. So d equals 5 is a candidate. What about d equals 6? D equals 6. This gives 36 minus 24 is 12. That doesn't work. What about d is equal to 7? 49 minus 24 is 25. Okay, so that works. D is equal to 8. 64 minus 24 is 40. So that doesn't work. What about d is equal to 9? 81 minus 24 is equal to 57. I think we're probably beyond or very close to beyond the maximum value that d could possibly be. So 100 minus 24 is equal to 76. So we did skip over a square, so we keep going. D is equal to 11. 121 minus 24 is equal to 97. D is equal to 12. 144 minus 24 is 120. And now, when we set d is equal to 13, we'll see that we have a problem. So 169 minus 24 is equal to 145. And this is greater than the next possible square. So any number above 13 that we sub in here, d squared minus 24, will be greater than the previous square. So it could never be a previous square. So there's only two values of d that work here, 5 and 7. So let's work with d equals 5 first. And I want to copy this whole expression. But the discriminant I've simplified, right? This is d squared times d squared minus 24. Okay, so d is equal to 5. I have a is equal to negative 30 minus 25 plus or minus square root of 25 times 1, all divided by 6. So a, if I take the negative sign, it's not an integer. So I have to take the positive sign. A is 0. So this gives the three-term sequence 0, 5, 10. We can verify that this works. The sum of the squares, 25 plus 100, equals 125. and that's also equal to the middle term times the common difference squared. So this 10 is in fact the third term in that sequence, okay? So now let's try A equals 7, or sorry, D equals 7. A is equal to negative 6D minus D squared plus or minus D squared times D squared minus 24 divided by 6. Okay, 49 minus 42 is 7, plus or minus 7 times 5 divided by 6. 7 plus or minus 35 over 6. 7 plus 35 is, so this is 42 over 6, or 35 minus 7. Well, it doesn't, 28, right? 28 over 6 won't be, negative 28 over 6 is not an integer. So we can eliminate the negative sign. So A is equal to 7. This gives the sequence 7, 14, 21. And let's verify again. 7 squared plus 14 squared plus 21 squared. Well, this is 7 squared plus 4 times 7 squared plus 9 times 7 squared, which is equal to 5 plus 9, 14 times 7 squared, which is the middle term times the common difference squared. So the next term, the only other third term in the sequence is 21. So 21 plus 10 is equal to 31. And that'll be my final answer. Things ended up working out so nicely here that I find it unlikely that I have an arithmetic mistake. The only thing I can think of is maybe somewhere in my logic I went wrong and I'm missing a sequence. I end up that there are only two of these special sequences, 0, 5, 10 and 7, 14, 21. But maybe I did some arithmetic incorrectly here somewhere and something else actually works out. But if I did the arithmetic correctly, none of these are perfect squares. So I don't have to worry about that. You know, even if we go one higher, D is equal to 14. That's, I believe 14 squared is 196. Minus 24 is 172. Yeah. Yeah, it was a nice problem, somewhat intimidating at first, you know, but a couple things that I typically like to do here when given what is not exactly a word problem, not exactly what I would say is a word problem, but more or less a word problem. Just take all the information you're given and write it down into mathematical statements, which is pretty much just, you know, you're concerned with a relation like this between A and D. Also keep in mind that we have restrictions on these numbers. At this point, I wasn't completely sure what was going to work, but you know, you got to try something eventually, and expanding this is a pretty natural thing to do. And then again, looking at this, I was on the verge of trying some guess and check, just try to guess some values of A and D that would satisfy this equation, and maybe you start to see what possible values are allowable. But I'm happy that I sort of just said to myself, wait a minute, this is a quadratic expression in A, so let's fix a value of D and solve for A and see if there's something we can come out with. And when you keep the information you're given in mind, that D is positive, it's an integer, and A must be an integer, that puts restrictions on what this discriminant can be. And that pretty much led to the final answer, more or less. A little bit more work, but that ended up allowing us to complete the problem. So yeah, 31 will be my answer, but if I have a mistake somewhere, I'll let you know. Thanks for watching.